welcome to the next session on finite element analysis. In this session, we are going to discuss about linear and non-linear FEA. We will discuss the difference between the two at every stages of FEA analysis. The key difference between linear and non-linear FEA lies in how they model the material behavior and deformations within a structure under load. First, we need to discuss about the material behavior, wherein we may assume that the material is linear, wherein it is not, and we go for analysis. So that is one thing which we need to take into picture. And the second is deformation. Suppose if you are going for a stress analysis of a bar, which is fixed at one end and there is a load applied on the other end. In that case, there will be some deformation also generated on the body. This deformation can be too large at times. Then we need to consider non-linear analysis. This is what we have already discussed in FEA analysis sessions. When we were talking about ANSYS problems, I have definitely taken you through these two concepts. So today we will just discuss the theoretical aspect of it as it is understood in FEA. Here are the primary distinctions between linear and non-linear FEA. So the first one is material behavior. When we talk about linear FEA, it assumes that material behavior is linear, meaning that the stress and strain relationship is constant and does not change with the magnitude of the load. Hooke's law, which describes linear elasticity, is commonly used. The assumption of proportionality between stress and strain holds throughout the analysis, regardless of the magnitude of the load applied. So we need to be very careful when we are talking about linear FEA, because your stress and strain are directly proportional. Load is not something which is causing the stress and strain to go into non-linear relationship. When we talk about non-linear FEA, it accounts for non-linear material behavior, which means that the stress and strain relationship changes with the magnitude of the load. So it is possible that after a certain load applied, which is after the elastic limit, if you remember the stress strain diagram or strength of materials, then after the elastic limit you see a upper yield, lower yield, then you see the ultimate stress generated over the body, and then finally there is a rupture. But necessarily after the elastic zone you find something which is plastic, that is a permanent set is already there in the material. So this is very important, that there will be some non-linearity to the system, which means the stress-strain relation will not be a straight line. It will be some sort of a curve. Non-linear material behavior may include plasticity, large deformations, hyperelasticity, or other non-linear effects that cannot be accurately represented by linear assumptions. You can see certain ANSYS videos that I have created where I have shown you clearly the difference between linear and non-linear FEA, wherein there was large deformation or plasticity introduced into the system, which means the system has lost its elastic abilities. So it will not get back to the same shape and size. It will show at least a small amount of permanent deformation in the body. So this is something which you need to understand. This is very important because when we go for ANSYS analysis, we generally assume the analysis to be linear by taking a material which is of linear type. So we completely ignore non-linearity and we go into the analysis, which will lead to errors into the FEA analysis. So if you want to get better results, more accurate results, then you should consider non-linearity also. The next one is deformation. Linear FEA assumes small deformations. The method is based on the assumption that the displacement of the structure from its initial configuration is small and the resulting deformations are within the range of linear behavior, suitable for problems where the structure undergoes small displacements and strains. So if the strain increases more, or rather I would say if the permanent deformation is coming into picture, then obviously it has lost its elasticity. And then you need to go for non-linear analysis, and linear analysis is not going to solve your problem. Non-linear FEA accounts for large deformations and geometric non-linearities. It is suitable for problems where significant displacements and strains occur, and linear assumptions may no longer be valid. Geometric non-linearities arises when the deformed shape of the structure significantly affects the distribution of forces and displacements. So I think this is very self-understood. This is what I'm trying to explain you with the help of material behavior and deformation both. That after a point, a material loses its linearity and then it will go into the non-linear zone. It could be because of material behavior where you have assumed the material to be linear, or maybe you have not changed the option of deformation to large deformation. So if you solve certain problems, you will see that when the deformation is large, the software actually gives you an error after the solution is obtained that there's a large deformation introduced, which means that you have assumed linearity and it is not. So at that stage, you need to go to the solution option and just change the solver option to consider large deformation, which means you are allowing non-linearity into the solution. Next is solver complexity, linear FEA. Solving linear systems of equations is generally computationally less demanding and faster compared to non-linear analysis. This is one of the reasons why we go for linear FEA, or we assume system to be linear, because it is less taxing for the hardware. Otherwise, it is possible that your system may go into hang mode if you use non-linear FEA. The governing equations are linearized, simplifying the solution process. Non-linear FEA. Solving non-linear systems of equations is more computationally intensive. Non-linear analysis often require iterative procedures to converge to a solution. Iterative methods such as Newton-Raphson are commonly used to handle the non-linearities. So you need to have a better solver, you need to have a better processor to handle non-linear FEA. And Newton-Raphson is the iterative method which is used for non-linear FEA. Now this works at the back end, so it is not something which is visible to you, but this is just for your information. Applications of linear FEA. Well suited for problems with small deformations and linear material behavior, where the response is predominantly elastic. Commonly used in linear static analysis, eigenvalue buckling analysis, and modal analysis. Now you can go through all the videos of ANSYS which I have created. There you will definitely find these analysis, and you will see that I have assumed linear FEA and solved the problem. Non-linear FEA, essential for problems involving large deformations, plasticity, contact, material non-linearity, and other phenomena where linear assumptions break down. Used in applications such as non-linear static analysis, dynamic analysis, and studies involving material yielding or structural instability. So again, there are videos that I have created on non-linear FEA as well. You can go through them. You will get a clear picture of what is to be done if non-linearity is encountered by solving, or how to solve for non-linear analysis in certain problems as well, wherein I have started with assumption that I'm going to use non-linearity and solve. So now we'll go for some key points of the session. In summary, linear FEA is appropriate for problems where linear material behavior and small deformations are reasonable assumptions. Non-linear FEA is necessary when dealing with significant deformations, material non-linearity, and other non-linear effects that cannot be accurately represented by linear assumptions. The choice between linear and non-linear analysis depends on the specific characteristics of the problem being analyzed. So there will be certain problems where you need to consider the non-linearity and solve. For example, there can be some non-linear static analysis which is encountered. Suppose if you are talking about the stress strain analysis, if you want to go for it, you can solve it for linear and non-linear both. There are certain dynamic analysis wherein you need to know the non-linearity. There are transient analysis where non-linearity comes into picture because the deformation may go quite high. So there are many problems wherein you need to talk about non-linearity, and linearity is not going to help you. The solution itself which is obtained in ANSYS will give you an error and show you that you have assumed wrong linear analysis and you need to go for non-linearity only. So with this, I end the session. I hope you understood the concept of difference between linear and non-linear FE analysis. If you have any doubts, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.